Hi, in this video, we want to look at imputing missing values with the missRanger package. All right, so the Ranger package is a random forest package. So in our, before the Ranger package, there was the random forest package. And Ranger, to a large extent, is a speed improvement of random forest. Now, it's not 100% true. There's more nuance to it than that. But for most people, the main advantage of Ranger is the fact that it's faster. Now, the random forest package is a very good package. It has a lot of utility in it. If you want to do things, if you have concerns other than speed for your random forest, like you want inference off of it, you want more support in other ways, the regular random forest package is a good choice for what you're doing. Now, the Ranger package, like I said, is mainly just a speed improvement. That is like it's the big change between the two. Well, our community took it a step further, and they set it up so that we can impute missing values with the Ranger package, so that it would be nice and quick and fast. And in my opinion, this is the best way to impute values when I'm not going to have to impute down the road later. So the advantages of this package is that, one, it's fast for the quality of imputation that you get, and second, you get pretty good quality for it. So, I think it's pretty good. Now, the major disadvantage about this is that if I have a training set and in the future I get a new scoring data, or after that I get a new scoring data or something like that, but the scoring data that I need to make a prediction on, I don't have yet, there is no clean, easy way to do imputation. What I have to do, I have to take that training data from before, tack it onto the new scoring data, and then perform imputation. And then that way I can get the new scoring data imputed like I want. Now, if I get new scoring data after that, then I have to do this process all over. That means I have to refit the imputation model over and over and over. So like potentially if I had month after month after month new scoring data, this could be repetitive. It's definitely going to be redundant. If it's a big data project, this may not be a feasible option. There would be better ways to handle this. So also a big advantage of this is that missRanger handles any type of variable that I've encountered. So you drop it in, you have missing values, it spits out a full complete data set for you. All right, so let's go ahead and look at the arguments first and foremost. So of course, first parameter is going to be the data. So it has to be either a data frame or a tibble, and I'm pretty sure that it won't accept a matrix. Now the formula, this one is an important one. What this does, the formula gives us control over which variables get imputed and which variables are used to impute. Now, so on the left-hand side, all the variables that are to be imputed, the variables with missing values that I don't want to have missing values for anymore, are on the left. And then all of the variables that I want to use to fill in the other ones is on the right. Now, if you look at the mice package, the mice package lets me pick and choose like the combination of imputed and the imputing variables. With missRanger, it's just one big formula. So every single variable that's getting imputed gets imputed by the same variables on the right. I only have one formula. If I want it to be more nuanced, then either I need to use like the mice package, or I need to do multiple imputation processes, which may not be the best way to go. Now, next one is the number of predictive mean matching. That's what it stands for. The number of predictive mean matching terms that we use. All right, so predictive mean matching, what it does is the model, gives us a modeled value, and then the algorithm goes through and it finds a value in the data that is closest to the modeled value. Well, what this K does, let's say I want to take the closest 3 instead of just the closest 1, closest 2. So this way, what it's going to do is going to give us something that is more similar to the actual data that we have. And predictive mean matching, one thing that it tends to do is it tends to not decrease the variance of our data set. So if I'm doing something like inference, if I'm doing hypothesis testing and I have to use imputation, which is very rare, but it does happen. If I'm in that situation, then the predictive mean matching tends to do a better job of not decreasing my variance. Now, max iterations, maximum number of chaining iterations. Seed, I strongly recommend that you set the seed before you do this because this is a random forest process, so I'm going to be using a random number generator. Verbose controls how much output we get, so we can have it as 0, 1, or 2. 0 for nothing, 1 is for a little bit, so it just kind of tells us the progress, and then 2 gives us more information about which variables were imputed by which ones. So when I do the formula, what's going to happen is I'm basically saying all of these variables to be imputed can be imputed by these over here, but that doesn't mean it actually works out. Not all those variables necessarily will be used in each of the receiving variables. So what will happen is that if I put a 2 here, it will actually give me feedback on which ones were used for each imputed variable. Now, return out of bag error. All right, so when you have a random forest, one way to get an idea of the validation statistics is to do out of bag error. My experience is that with random forests and with tree models, out of bag error tends to be optimistic compared to the validation statistic. According to the literature I've read, it's not supposed to be that way, but my personal experience is otherwise. I personally take a look at it, but I don't sweat this one so much. I usually use this if I'm trying to hurry and I don't want to bother taking validation statistics. For this purpose, this basically just gives you feedback on does it look like you have good imputation or not. In case weights, we can control the weights if we want. And then there's additional parameters. So here, what this is referring to is all other parameters in the Ranger function and within the Ranger package, we can grab onto and pass through. And so if I want to speed things up, if I want to improve the imputation, like I've got some more time, I can control what's going on. So like, for example, let's say I don't have time to run through 500 different trees for the modeling. I can reduce it down to 20 trees. All right, so now let's go ahead and run through an example. So once again, I'm going to be using the Nashville housing data set from Kaggle. And I'm loading the data here. Here I'm cleaning up the column names. And here I am rearranging the data so that the rows and columns are sorted by the number of missing values. This way, I find that it helps me understand like what I'm doing when I go through the Impute. If I see that there's an issue on the far left or on the far right, I have a better idea of what's going on because I know relatively how many missing values are in that column. All right, so what I do here is that I look at the data set. I go, okay, if I'm going to be trying to model sales price with this data, which ones are going to be the predictors and which ones have missing values? So I went through, I made V predictors is a vector of the predictor names. And this is something I almost always do when I'm doing real projects, is that I make vectors of the column names that I want to use for each different purpose. That way, down the road, when I want to grab it, I just type in the vector name instead of having to give the entire list. Now, I took a look and I found which predictors had no missing values. Well, land use, sold as vacant, multiple parcels involved in sales. All right, so that means I have 3 complete vectors in the data set. Now, what about the incomplete predictors? Now, there are other complete columns in the data set, but things like address and ID numbers aren't going to help us. So those are not included here. And incomplete predictors, these are all of the predictor variables that I want to impute. All right, so there's a formula for imputation. So what I'm going to do is I'm going to go ahead and I'm going to take all of the incomplete predictors are going to be on the left-hand side of the formula, and all of the complete predictors will be on the right-hand side. Now, so when I do that, this, you'll notice, is all of the incomplete predictors are on the left-hand side of that tilde. All right, so this paste function right here with collapse equals the space plus space gives me the left-hand side right here. All right, so these are all the variables whose missing values are going to be imputed. I'm going to take surrogate values, best guess values, and replace those missing values. On the right-hand side of the tilde, I have the complete predictors, and these are being used. This is the data used to fill in the blanks on the left-hand side. Now, what I could have done, I could have taken all the predictors on the left, all the predictors on the right. Okay, if I have a complete predictor on the left, the missRanger function is going to check and see, is there imputation to happen? Well, that is a step that I don't need to have happen, and that can take a while. So maybe that really won't take a while, but I'm going to slow down the process. If I want to have it efficient, I don't want to have crap on the left-hand side of my formula. Now, I could definitely have had my incomplete predictors on the right-hand side also. That is definitely a reasonable option to go with, but I was just playing around with it, and it took longer than I felt like waiting for, so I went ahead and went with this. If this was a real-life project and I had the time, I would probably explore using some more predictor variables on that right-hand side to get better imputation. But for the purpose of making the video and getting it out to you, I just went ahead and went with the complete predictors only. All right, so now what I'm going to do, I'm going to impute using the ranger function. So something I always do, I always set the seed, just set it. I really should set it inside ranger, but for this example, I wanted this to be as simple of a demonstration as possible. So I gave just the minimum stuff. I gave the data and the formula. That's all. That is the minimum stuff I need to pass in. You notice I didn't say anything about verbose. I didn't say anything about setting the seed. I didn't mess with any of the other parameters. Just so that this is just the default settings, easy peasy example, just so you can see how to execute. All right, so here's the output. And I believe this is a verbose level of 1. And we can see that it did 5 iterations. And it combines all those iterations together. So it repeats itself 5 times. And these dots, if you run this in R, you'll see the dot, 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 dot as time progresses. It'll go dot, then another dot, then another dot, another dot, another dot. And that's showing you the progression of it as it goes through. All right, well, now let's go ahead and play around with the parameters just so we can see another example. Oh, and I am storing everything in a list that I'm calling list imputed because it's going to be my imputed data set. All right, now I'm going to go ahead and call this one predictive mean matching because I'm going to go ahead and use predictive mean matching with 3 of the closest observations. I'm setting the C to 823, that's UCF on a telephone. Verbose is 2, so it's going to give me more output to read. And I'm going to go ahead and get the out of bag error. So basically, I'm just changing all the other parameters just to change them, really, just so that the video can demonstrate. All right, so when I say verbose equals 2, the biggest change is that you can see all of these aspects of, you get all this output, and it is hard to read, but so we have variables to impute. We have variables used to impute. And then each of these is the out of bag error on that imputation model. So here we can see that we have 0.29 for city imputation out of bag error, and we have about the same down here. And we can go through. We can see that land value changes. Oh, now something about this that it goes ahead. Oh, actually, the property C. What was property C? I misspoke. Let's scroll up. Please work with me. All right, property city. All right, so property city has out of bag error on first iteration of about 0.3. And then the same on the second iteration. Then city has a 0.2 out of bag error. And so I can look through. So it doesn't line up very well, but here's property city, then city, tax district, acreage, land value, building value, and then it keeps on going down the line. So one thing that's jumping out at me is that the out of bag error for the numbers is much larger. But remember, that's a different way of measuring the error. So here, this is going to be the percent of time, or the fraction of times that it got the categorical variable wrong on the random forest building. And then here, this will be either mean squared error or mean absolute error. All right, now, one thing we can also do, we can also just impute with a single tree. Now, why would we want to do this? Well, first of all, it's faster because there's only one tree. The default, if I remember correctly, is like 500 trees. If I remember correctly, for Enterprise Miner, it's 50 trees. You know, so the idea with random forests is that we're allowing a lot of inaccuracies, but things average out, so it doesn't matter that we have the inaccuracies in the model. That's kind of like the big idea. We have more variance than we should be, but the average, the predicted value, is actually solid. All right, and so here I have the number of trees as 1. Now my sample fraction is I'm using the entire data set. I'm making sure the tree depth goes to a maximum of 30. It's much lower on the default setting. And I adjusted the minimum node size. I think the minimum node size is 1 by default. I can't recall exactly, but we can look it up in the help documentation. But you can see that basically I'm adjusting this so that these are better parameters for a single Cartesian tree. And here we get the output, and we can see that, you know, it only took 3 iterations to converge. All right, so if I'm doing my imputation and it just takes too darn long, right? So this is a real problem. I've encountered this problem, not with the Ranger package, but with other packages like with Random Forest. This will be an issue that you will run into. I've ran into it with stochastic gradient boosting and extreme gradient boosting in particular. So it's just taking too darn long, and I need to get my project done. I just don't have time to be spinning my wheels on this. I need it to work, and I need it to work fast. What do we do? Well, missRanger is based on iteratively fitting random forests for each variable with missing values. So like by default, we've got 100 trees for each imputation model, 500 trees for each imputation model. I mean, that's probably more than we really need. All right, so I mean, that means that there's going to be a good number of calculations. Also, when I talk about random forest, one of the features of random forest is that random forest, the trees are too deep. Stochastic gradient boosting, the trees are too shallow, and then decision trees are just right. And that's actually part of the structure. So by having random forest trees too deep, that additional variance actually evens out and works out good because I have so many extra trees. Stochastic gradient boosting, because of the gradient aspect, I need shallow trees or I'm going to overfit. And then regular trees, we want it just right. We want that Goldilocks problem. All right, so in this case, we have deeper trees than we really need, and we have more of them to deal with like that variance aspect. Well, what could we do? Well, we could use less trees, so we could set the number of trees down to 50. And, you know, honestly, a lot of times a single tree can do imputation pretty good, because remember that when I'm imputing missing values, this is surrogate data. This is just a best guess. And if I can get just as good of a guess off of 1 tree, 10 trees, do I want to bother with 500 trees? Probably not. So, you know, 1 tree might be sufficient. And the number of iterations will converge faster with fewer trees, which is kind of an interesting aspect. So if I use fewer trees on each iteration, then each iteration will take less time to compute, and I'm using fewer iterations because I have fewer trees, means that once again, it's going to take less time. So this is a huge advantage. Now, one thing we can also do, and this is a good choice if you have big data, we can also use a smaller fraction of our data. So one thing about random forest, the reason why it's called random is you do a random bootstrap sampling on your data on the rows, and then you build a decision tree off of that bootstrap sample. Okay, well, if I have a huge data set, I could reduce down my sample fraction and really not risk much. So let's say I reduce it down to just 10%. And we could use a less greedy split rule of extra trees. So there's different split rules for each type of data, and the help document spells out each of those. In general, extra trees will be a faster choice. We can also make the trees shallow. So we can go with a max depth of 6. So what that means is the trunk, I believe in this definition, starts at 1, but then after 5 splits, it's done. And so the tree would be a lot simpler, a lot shorter. And since it's surrogate data, we're probably going to be okay on any loss we have from not going deeper. Also, another way is to make sure that each node in the tree has more data points. That's in a way similar to making sure the depth doesn't get too deep. But here we're using the data in each tree to decide if it's going to go any deeper. Here, this is kind of like a hard cutoff. This is a cutoff depending on what we see with the data inside the nodes. This is hard absolute stop declaration. We can reduce the number of iterations to 1 or 2. We can use fewer variables to impute. All right, now this is what I did in this video, is that you notice I only used the complete cases. I didn't consider the incomplete cases at all for imputing for being used to impute. So by doing that, I was able to speed up this process. And also, this is one that's not in the help documentation, but almost everything runs faster with numeric data than categorical data. Just keep that in the back of your mind. Now, the reason for that is because for tree models, it's simpler and easier to split the data when I have ordinal or numeric data. If I have categorical data, if I talk about subsets of categorical data, I have 2 to the n possible subsets. So if I'm going to be splitting, I have 2 to the n minus 1 possible subsets or splittings to figure out for my levels. And that can take a long time to compute. If it's ordinal, it's not as bad. It's going to be n minus 1. If it's numeric, it's going to be n minus 1 also for the unique levels. So numeric and ordinal data will be faster inside trees, specifically numeric. All right, so here I want to go through another example. I call this example fast. And so I'm reducing down the number of trees down to 20. I've reduced my sample fraction to 10%. I'm using the extra trees split rule. Max depth is 6. And minimum node size is 10,000. I don't think this is going to apply to this data set because of its size. And then maximum number of iterations is 2. So it's possible that the averages do not converge when I use them. And it used both iterations. And so also remember, whenever I'm building models, if it takes a lot of iterations for things to get how I want it to be for it to converge, that's a sign you have bad model structure. So up here, 3 iterations, that's pretty short. That's pretty good. Here, 5 iterations, anything under 10. I mean, for virtually any algorithm, you can say that that's a good way to go. But if you see that it takes 1,000 iterations for it to converge, you probably have bad model structure. All right, now the Ranger package, or excuse me, missRanger package, also has univariate imputation. All right, so it's possible that we really don't have any good variables to impute another variable. In that situation, univariate imputation is one of the better options to use. And the missRanger package lets us do it. And I went ahead and just put in random number seed in there. So here, what you have to do, you have to specify the data set. You have to specify a character string saying which variables to be imputed. All right, so now that I've got complete data, so at this point, I've got imputation with the default settings. I got imputation with predictive mean matching. I've got imputation with the fast parameters, imputation with a single tree, and then the univariate. Okay, so I have 5 imputed data sets. I want an idea of which of these look like they would be the best for making a model predicting sales price. So what I'm going to do, I'm going to predict the log of sales price using a linear model and the imputed data. So on all 5 data sets, I'm using the same model structure. The only difference is the data. And so I'm going to use the performance of the different models to evaluate how well I did my imputations. Now here I'm just doing it on the training set because I'm lazy. If I was doing a real project, I would do a validation set and possibly a test set. All right, so here is my predictive model. So I'm taking the log of the sales price, and I'm saying that this is a dependent variable on all of these independent variables. And now what I'm going to do, I'm going to build a linear model on each of my 5 imputed data sets using this formula for the log of sales price. And then what this code does, this code goes through, I make a prediction on the linear model. I take the log of the sales price. So remember, the model is modeling the log of the sales price, not the sales price itself. I'm going to subtract off the log of the true sales value. I'm going to take the absolute value of it. And then I'm going to take the average of the absolute values. Remember that if I do regression, the average of the residuals is always 0. So I need to take the absolute value before I take the average. And I'm going to store this in a vector. I'm going to call it vector mean absolute error, MAE. And I go ahead and sort it. All right, so when I do that, I see that the fast parameters gave me the best model. Then after that was a single tree, then default settings, then predictive mean matching. That surprised me when I saw this. And then the univariate. All right, so one thing I like to do, I always like to do univariate imputation and just see how does that perform. Because if I get a poor model result from univariate imputation, I probably have like bad imputation with the model. So if I see that these are close, so like let's say I had a 0.46 for my imputation model, and then I see univariate, I have 0.47. That's not much of a difference. If this was my model that I had, I didn't have the other ones, I wouldn't trust this one because it's so close to this. But this is enough that I think I would go ahead and choose the fastest parameters for that. All right, well, that's all I've got for you. Take care and goodbye.